Hi everyone and welcome back. Today we're going to go ahead and continue our lectures with work and kinetic energy. We're going to begin our discussion on work. So work is done on an object when energy is transferred, to that object, okay? It is also done when a force acts on something that undergoes a displacement from one position to another. And that is what this equation states here, okay? So this is some kind of change in work is equal to the dot product of the force and the displacement vector, okay? And we learned last time that, we learned a while back actually, that the dot product between two vectors is also equal to the magnitude of the two multiplied together times the cosine of the angle between them. Give me just a second. All right, sorry about that. And work is done, if work is done by a force, it is the integral of the force with respect to displacement along the path of the displacement. Okay, so graphically you can see that here. If we have some path from A to B, okay, and we have some sort of force and displacement vectors and the angle between them, theta, okay, we can determine the work done by this force, okay, and that is going to be the work of A to B is equal to the integral of the path AB is the dot product between the force vector and the displacement vector, okay? So using this, we will look at in a few slides some examples, okay, of how to use this. Now, one thing to note is the units of work, okay, and that is going to be in joules, which is Newton meters, okay? So 1 joule is 1 Newton meter, and that makes sense because force is in newtons and displacement is in meters, okay? All right. So let's go ahead and move on, going into the simplest first example of this, and that's going to be, when work is done by a force that is constant in magnitude and direction. So what that means is the force is not dependent on the direction or the coordinates. Okay, so it just is some magnitude, okay? So what we have here is exactly that. We have the work from A to B, okay? And because the force is not dependent on our direction, we can pull that out of the integral. Okay, so now we have f dot integral dr, and we can take this integral and solve it. And so we have f dot r at b minus r at a, and these are still vectors, okay? And again, using what we just did in the last slide, we can say the magnitude of f times the magnitude of rb minus RA is equal to, times cosine theta, okay? So this is going to represent our work by a force that is constant in magnitude and direction, okay? All right, we can also do this in Cartesian coordinate form. So let's go ahead and do that. So what we'll do is we'll start with our work is equal to our integral from A to B, f dot dr, okay? Now, we're going to go ahead and state that f is equal to f sub x I hat plus f sub y j hat plus f sub z k hat. I do apologize if you hear little tippy taps in the background. That's my dog running around me. She thinks it's time to eat, but it's not. All right, so let's go ahead and put that in here. So we have our integral from a to b, and our f vector, which is f sub x I hat, plus f sub y j hat, plus f sub z k hat, dotted into dr is going to be dx I hat plus dy j hat plus dz k hat. Whoops, there we go. Okay, so dr is just this. Okay, that's what that represents. We're taking each individual dx, dy, and dz. Okay, so now what we'll do is we'll go ahead and apply the dot product here. So again, we still have our integral. Okay, now we'll apply our dot product. So this is going to be f sub x, and this will be dotted into the first term, dx, and this is I hat dotted into I hat, which is 1. Okay, now hopefully you guys remember from our dot products, if I take f sub x I hat and dot it into, say, this second term dy j hat, okay, if I did that, then my I hat dot j hat would equal 0. Okay, so hopefully you guys remember that from a few weeks ago. Okay, so that would be 0, and then the next one would be 0. So now we're on this term. So we have f sub y j hat, and that will be non-zero here, times dy, plus our third term here, f sub z, dotted in, and it's going to be dz. Okay, so now this is our integral, and as you can see, it is now not a vector anymore. It is a scalar, which makes sense because work is a scalar. Okay, I forgot to mention that in our last slide here. Work is scalar. Okay. All right. So let's go ahead and keep going. So now we will have 3 different integrals. I can just write it right here. From a to b, f sub x dx, plus integral from a to b, f sub y dy, plus integral from a to b, f sub z dz. Okay. So again, if this is a constant force, then our integrals here will be pretty simple. Okay, it'll be f sub x times x, and that'll be from a to b. Okay, that's our first integral, and it'll be similar in the other two. Okay. All right, so this is what we have so far. Okay, now I'll need to continue on the next page here. So our work from a to b is equal to f sub x, and remember it is x at b and a, so x at b minus x at a. Okay, and it'll be the same for the other two, but now we have y and z. Whoops. Z at A. Okay, so this is our work in Cartesian form. Now what you may notice here is that if we look at this, we see f sub x, f sub y, f sub z. Then we have this x x sub b minus x sub a, this y sub b minus y sub a, and this z sub b minus z sub a. So there's a pattern here. So we can say now that this work a to b is f bar dotted into r bar at b minus r vector at a. Okay? Hopefully you see this pattern. Okay, so again, remember we started with the fact that we had an integral from a to b of f dot dr. Okay? And we ended up with this form. And again, this is work done by a constant force, right? Constant force in magnitude and direction. In magnitude and direction. Okay? All right. So let's go ahead and move on. Okay? So we are again looking at work done by a constant force. And we want to know which of these three has done work. Okay, so which of the following does work? So if we look at part A here, where there's this guy pushing on a lawnmower, okay, and at some force at this angle, and the lawnmower is moving with some displacement here, okay? We do have some sort of work going on, right? Because work is equal to force dotted with the displacement, okay? So we do have work here, okay? Now, if we are looking at this woman head on, okay, we're looking at this person head on, and she is holding this purse or bag. Kind of looks like a computer bag from this side. So we'll say it's a computer bag, and she is holding it up with some force, okay? But it does not have any displacement here. Okay, so the displacement is 0 since it's not moving up or down. Okay? So, again, with this formula here, okay, our work then would be 0, right? If there is no displacement, that means that there is no work done. Okay, so this would be 0 joules. Okay. All right, let's look at this last scenario. The same person, but now we're looking at, again, her force this way, but now we're looking at her from side view. Okay, and we do have some displacement here. Okay, so there's the displacement, and the angle here is not some arbitrary angle. It is 90 degrees. Okay, so our force vector and our displacement vector are 90 degrees from one another. Okay, now if we plug that 90 degrees into our cosine in this formula, cosine of 90 degrees is 0. Okay, that means that, again, the work done here is 0 joules. Okay, so just watch out for that when you're going through problems. Make sure it makes sense. Okay, all right, now we're gonna, well, we'll hold off on this example till the next video. So I will see you in the next one, and we'll go ahead and continue with the lecture as well.